Good morning, afternoon, or evening, everybody, depending where you are. This is Panama Bartholomew with the Building Decarbonization Coalition, and welcome to our webinar series, the Building Decarbonization Coalition Presents. Today, we have a fantastic presentation. We have Shawn Oram from Ecotope talking about how you design all-electric, super efficient central water heating systems. We're really excited about today's topic. When you look at probably what is the biggest knowledge gap within the building electrification space, central water heating has to be towards the top of the list. It's definitely very doable by the great engineers that work on buildings around the world, but they've never had to do it, and it's very different than working with boilers. And so it's a knowledge share, and that's what we got today. Shawn is a global leader in the design of these systems, and he's going to lay down some knowledge for us today, as well as give us an update about where the industry is going and some great new tools that are coming out that are going to help. So just a little bit about who we are. The Building Decarbonization Coalition is a nonprofit. We're based out of California, but we do work all over the country and soon all over the world. And we're a coalition of energy providers, utilities, CCAs, and the like, manufacturers of heating equipment, the design and construction community, local governments, and nonprofit organizations. And we work together on both policy and market solutions to push building decarbonization with the goal of fully decarbonizing the built environment. We released a roadmap that describes what we mean by full decarbonization of the built environment, focused initially on California's buildings in January of last year. And we called for a series of measures to be taken on, zero emission codes for the residential and commercial building stocks by 2025 and 2028, respectively. And then the implementation of policies that lead towards a drawdown of emissions from the built environment so that we're to 100% emissions-free buildings by 2045 or sooner. Implicit in that is the sale of heat pump technology. We really think that electrification is the way to go on building decarbonization. And so if we're going to be decarbonizing buildings, we really need to be phasing out gas appliances and phasing in high efficient electric appliances and heat pump technology for space conditioning and water heating. So underneath those numerical goals, we laid out 5 principles that are going to need to be realized within the marketplace if we're going to meet those numerical goals. And those are up on the screen. And in short, it's really building awareness across the board, policymakers, the design and construction industry, owners, occupants, making sure that customers are receiving a good value proposition from electrification. And so not only the capital cost, but also the operating costs of all electric building is providing a good value to the customer. That building decarbonization provides a really strong value proposition to installers and builders as well. This is not going to work if you're making less money on electrification than you were on natural gas design and appliances. And then making sure our supply chains are robust, ramped up to the rate that we need for this transition, and that we've gotten barriers to the supply chain out of the way, whether that's small enclosures for where we want to put some of these appliances, undersized electrical panels, et cetera. And then lastly, we need to align policies in order to meet other goals. We need to make sure that our goals that are driving decarbonization actually are aligned with our goals around construction, low-income housing, school construction, et cetera, so that we don't have cross purposes of policies so we can achieve the first 4 goals. This webinar series clearly fits under that first goal. And so we implement a whole series of programs and initiatives in partnership with our members for each of those goals. And this webinar series is a part of that first goal, is how do we really expand awareness, not only the benefits of all electric design, construction, and living, but also to the industry, how do we go about doing it? And so what we do is we bring in national and global leaders like Shawn to share with us the knowledge about what's happening in the industry and how we can move forward. And today's topic is on central water heating design. One of our next webinars coming up is with Peter Rumsey from Point Energy Innovations. He's a mechanical engineer, another global leader in design, in green building design, and more recently in all-electric design. He does fantastic projects for really big and really small clients. He's taken his house all the way electric, and so has some great pictures of that experience. And he's going to be talking through us about the engineering of all electric buildings and some of the design challenges they're seeing right now, some of the cost implications of all electric design, and some of the projects they're working on. So a fantastic speaker, a great engineer, and you do not want to miss that. So you can go to our upcoming events website, which you see linked at the bottom of the screen if you want to hear from Peter about his take on the industry right now, and then engineering, what's going on in engineering for all electric buildings right now. So just a couple logistics before I turn it over to Shawn. You are all muted. We had about 340 registrants to the webinar, so thank you for joining. We ask that you ask your questions via chat, just because we have so many folks. We can't leave the lines open, and we will we'll ask Shawn to answer them at the end of his remarks. Looks like we didn't update the slide. The webinar is being recorded. Shawn, today you're going to be known as Donna. The webinar is being recorded, and members of the coalition can access the recording on the member part of our website. It's one of many great benefits that you get from being a member of the coalition. We have incredibly affordable rates for membership, and it's a way to be able to get engaged with other leaders in the electrification movement and to work together on what are the most vexing problems within building electrification, so that we can overcome them through sharing our resources and make it easier for all of us through that collaboration. So I would love to have you join us. If you want to check out what membership looks like, you can look on our website, buildingdecarb.org/join, for that information. I am now going to stop sharing, and I'm going to allow Shawn to share his screen, and I'll do a little introduction there as he does. So Shawn, why don't you start sharing your screen? Shawn, if you go to events on electrification or hot water, Shawn is there, and Shawn is presenting. Shawn is moderating. Shawn is dancing, and Shawn is drinking. He's good at all those things, and he's an excellent designer, and also that with customers about how do we actually get the stuff to work. We got to get it beyond the talk and into the work, and Shawn's a perfect person today to talk to us about what is the cutting edge and the state of central water heating design right now. So Shawn, thank you so much for joining us on BDC Presents, and please take it away.
All right, thank you, Panama. Great introduction. And again, Shawn Oram with Ecotope, Director of Design and Engineering. We've been working on central heat pumps for about 10, 11 years. So I'm happy to kind of share with you mostly kind of an update on what's happening out in the world, kind of behind the scenes, and just kind of show you some of the stuff that's being developed. So I'll try to cover everything, and again, as Panama mentioned, save your questions for the end, and then we'll have some time to kind of go through any of those. So here we are. So quick run through the agenda for today. We're going to do just a quick review of heat pump water heating, kind of the important parts. I know a lot of this folks have seen before, but I'll just reiterate because they're still important points. We're going to talk a little bit about the technology innovation roadmap. This is pretty crucial to making this transformation at scale in the time frame that we're being tasked to do this. We'll also talk about a new initiative called the Advanced Water Heating Initiative. This is an exciting group, and it's a good combination of resources. Somebody's unmuted there. Let's see.
I'll deal with it.
Okay, Heat pump water heating tool development. So this is an area that I want to kind of show you. There's some exciting stuff happening there behind the scenes. We'll also touch a little bit on the prescriptive heat pump water heater design specification that's now part of the Title 24 approved packages for central heat pump water heating. We'll touch a little bit on some of the packaged plug and play systems and kind of show you how the technology innovation roadmap kind of works and plays into that. So first part, we're going to just touch on some heat pump water heating background information. We looked at about 12 buildings in the Pacific Northwest, and this was sort of the end use energy breakout, domestic hot water being the single largest end use. The domestic heating was about 15% in a class of buildings that we looked at, while the temperature maintenance or keeping the lines hot was about 10%. And so both of those together make up the central heat pump water heating load. A hot topic these days are the refrigerant phase out that is looming. The global warming potential limits of 700 will likely be required in about 3 to 5 years. So this chart shows kind of the range of current refrigerants being used in HVAC and DHW heating, and this line 675 and up, those are kind of the next class of refrigerants, and I'm sure there'll be others that come aboard. But this is one of the big challenges with what we're looking at, is because we don't have a lot of gear, a lot of equipment in this kind of low GWP category, though the message is getting out and manufacturers are working on this. We do have some equipment, and so we'll kind of talk about how this transition will impact kind of the whole. So there's two transitions. There's the global warming potential, as well as the big transformation into all electric. And so this will be sort of an important topic, and folks are working on this very issue right now. I'll also touch, so the other part here is that there's really two types of heat pump technology for heating hot water. It's really single and multi-pass. And so single pass will heat all the water up in a single pass. So 50 degree entering into the heat pump, out will be 140. That's the system on the left. The system on the right is called a multi-pass. This is very similar to how a boiler works and hot water storage tank. These heat up the water in about 10 or 15 degrees with each pass. Both of those technologies are currently available. They should both be an option kind of moving forward. And so designers can choose either single or multi. The single pass products align well with some of the lower GWP refrigerants. And so there's a lot of focus on that, but the multi-pass have their advantages as well. And so right now, you know, the industry is kind of all over, and we're trying to focus the attention and the research on these two technologies. I do want to touch on what we call a loop or a swing tank with single pass. This is really important because it plays right into load shift, as well as maintaining efficiency with single pass devices. And so the concept that we're showing here is we've got a heat pump on the right, we've got a primary storage tank, and that storage tank is really sized for kind of your peak draw, which happens, and I'll show you a profile, but it happens usually in the morning rush and in the evening. And one thing that we've discovered with single pass equipment is you cannot run warm return water through that without significantly degrading the performance. And so this swing or loop or swing tank is a concept that allows you to essentially reheat the circulation water without it touching the heat pump. The idea is you pulse really hot water through this swing tank, and that there's enough temperature there to also heat the recirc as well as supply the domestic hot water load. This is a quick graph of this principle in play. So the graph on the bottom shows the swing tank temperature, and the graph on the top shows the flow rate through a building. This is 2 days. And we can see that the flow rate through the building will actually pulse and heat up the swing tank. And so that's what we're after. Oops, pardon me. Okay, so this is a really important concept because it allows you full COP and full performance on your primary water heat, and you'll get that same COP through the temperature maintenance. So this is a really key sort of design principle when you're designing with single pass equipment. To reiterate, there are two loads in any central heat pump water heating system. There is a primary water heating load, and there's the temperature maintenance. And so the primary water heating is just that. You're heating water for use. You're making the cold water hot. And this system is sized for around 16 to 22 gallons of DHW per person per day. On the temperature maintenance side, this is really just keeping the line primed. And the losses here, this is an area that needs obviously more research to understand what the range of values should be, but we've found in the field between 40 and 120 watts per apartment is the metric we've been using. This is an important number because we've got to continue to drive down these temperature maintenance losses because they make up a significant fraction of the total load. And just to kind of discuss, so the big picture, high level strategic goals are to essentially make heat pumps the standard practice in new construction and in retrofit. And we want to do this in 3 to 5 years. So this is a very aggressive goal, and there is planning in place to realize this. But part of what we're trying to deliver are COPs of 3.0 for heat pump water heating for domestic hot water heating loads. We want to use low GWP refrigerants. We want systems that are plug and play. We want them to be cost effective. They need to be reliable and have redundancy built in, and they have to have the ability to do load shift. So that is kind of the standard high level goals for central heat pump water heating transformation. I want to talk to you about a new group that has just formed. It's called the Advanced Water Heating Initiative. And this is a group run under the Building Decarbonization Coalition. NBI has a major role in this group. And what this essentially is, this is really exciting. This is kind of a gathering of resources because what we found is it's not just California. It's actually everyone is working on this. And instead of doing consulting for Canada and doing consulting for Oregon and Washington and California, the idea here is to pull all these resources together and align around an initiative, a very aggressive initiative to make this transformation happen. You can see some nice charts that NBI put together about, here's about this, the pace at which we'll do this transformation. And so we can see the 2020 and we can see this curve. We're going to transition from central gas to central hot water, heat pump water heating. NBI's website has more information on this. There's the transformation approach down there. I'm not going to go through it all, but it's essentially combining resources. And there are 4 major working groups in the Advanced Water Heating Initiative. There's the 120 volt unitary heat pump water heaters. There's the 240 volt unitary. So the 120 would be the retrofit, 240 would be new construction and or retrofit if the power was there. Third is the central heat pump water heating, and the 4th is connectivity and controls. So this was identified. These are kind of the 4 top key groups, and they're all sort of working together. So Bonneville Power Administration has been integral in the support of heat pump water heaters in the Pacific Northwest. They've been very integral in supporting some of the early work that we've been doing. They are actually the right people, and they are leading the Central Heat Pump Water Heater Working Group. And this is sort of the short-term tactical goals right now on the ground. This group has just gotten started. The membership is increasing, and so if you're looking to try to capitalize on a lot of this work, then this Advanced Water Heating Initiative is a really great group to be a part of. But what the work that's happening now is we're starting to push this technology innovation model as a method to bring all these new products and this whole transformation into full deployment in the next 3 to 5 years. And so I'll talk a little bit more about that in a moment. But next thing is to expand the communication between all parties. So folks involved in this group will, we're all working towards the same goal here, as opposed to islands, everyone working on kind of their own thing. The other big priority is to expand the CBEC RES simulation tool to allow for additional heat pump water heating technologies. Namely Colmac and Nile single pass are sort of the next up. Right now, there's currently a Sandin path forward as well. Also, another priority is to expand CBEC RES to allow for multi-pass configurations and equipment. And one goal that's been identified is to essentially use the existing high GWP refrigerant equipment as a bridge while the low GWP equipment is developed and brought into the market. And I'll talk a little bit more about that in a moment. There's a PG&E test lab. Right now, they are currently testing a wide range of installation variables. This includes the handling of the hot water circulation and some of the control settings. So this work has started up. The lab is back in operation as much as COVID allows it. The other high priority here is to create an open source free sizing tool for heat pump water heaters with support for designing for load shift. This has been a kind of a big focus, but there's been a lot of folks trying to understand how to actually go about designing these, and we see a big hole there. And so soon, and I'll show you some more of this, soon there's going to be a tool for everyone to use. So that's really exciting. And we need to continue to advocate for expanded research on temperature maintenance, system losses, and load shapes for a range of commercial buildings. So right now we're kind of focused on the large and end use, large load, multifamily loads, but there's certainly a lot of other hot water loads that need decarb considerations. This would be commercial kitchens, dorms, which are similar to multifamily, and any number of other hot water, high hot water usage end use loads. So one of the key pieces here that we talked about is the technical information is actually quite critical to the adoption pathways, because as it turns out that, the heat pump water heating is it's a little bit different beast than kind of what's traditionally in play, electric or gas. And so there's a lot of technical innovation that happens. And one thing that's really important is to make sure that we're all talking the same system metrics so that we have predictable outcomes. This would apply to both policy, to both the users, as well as grand market adoption. But it's really important that we're all kind of talking the same language when we start talking about all of these specifications in central heat pump water heating. Another thing that's become quite apparent is that in order to get the policy development in play, that we've got to attack this thing in kind of more of a parallel path. And so there's been a lot of work on how the kind of framework is going to happen. But what we essentially have, or we have a bunch of equipment available now for heat pump water heaters. We have a lot of equipment that's overseas that we need to bring in, and we don't know much about this equipment. And so what we've learned early on is if you just go and install this equipment into buildings, you're gonna be dealing with a lot of stuff and a lot of learning, and that's what we did early on. And so we've developed kind of this process called the technology innovation model. And for each of the different equipment manufacturers, what we found mostly in going, we're doing this now on a couple different products, but if you follow this kind of key step, there's a feasibility study, there's an application testing. And so you're doing lab testing, you're doing feasibility on how this thing installs, any code barriers. There's demonstration projects, there's M&V, there's system metrics. And along this step, or along these pathways, you're kind of feeding into the other parts of what needs to happen. And so on the policy development, it's really getting this information into the Title 24 program so that we can see the advantages heat pump water heating can have on kind of energy use and carbon impacts. There's also the whole market side of this, and how we deploy this stuff. So you can see there's pilot projects, there's best practice guides. And so this work is currently being set up and this problem is being attacked at a parallel level. And so in order to make this happen in 3 to 5 years, this is sort of the approach that we've taken. This is getting into a little bit more of the technology innovation model, but there's basically the manufacturer engagement. And so there's the feasibility studies, there's the development assistance, and we do the applications testing. And then we can see how this would transfer down into more of the needs. And right now, because heat pumps are kind of a new beast in terms of central, there's a lot of stuff that we currently don't have, tools. We don't understand all of the equipment that's available now, how it actually performs. So it's hard to actually model and give the right credit for that. In terms of the tool development, there's sizing tools, there's temperature maintenance sort of modules, there's load shift modules, and there's performance simulation. And so a lot of the tool development is happening in the background. There needs to be more research on temperature maintenance, so we understand more about the losses. So that work is continuing to be structured. And so, but what this really allows us to do is to actually bring on new products into this industry and make sure we understand them and get it right the first time. Because the last thing we want to do in trying to push this industry is to introduce products that have problems, and that is a good way to kind of destroy a program. And so this is really important. And so we've got a team together with this advanced water heating initiative to really go forward and aggressively attack this in a methodology like this. So now I'll talk, so in terms of the current heat pump options that we have available for central heat hot water heating, there's actually quite a few available now. This is sort of the list. It doesn't include everything. There's certainly others, but these are kind of the most popular these days. So the ganged up 134A integrated residential units. This is an approach where you put several sort of residential integrated heat pump water heaters together and then feed without recirc. You're feeding kind of close proximity apartment units off of a single kind of semi-decentralized bank of integrated units. The next option would be kind of the sand and CO2, the ganged up, and this is also aligns with the Title 24 prescriptive design. Colmac and Nile both have single pass central heat pump water heating equipment and controls figured out. So those are two additional options. The multi-pass 410A products are out there, and Mitsubishi's got a CO2 that's currently in pilot testing phase under the technology innovation model. So out of the gate, what we have now to work with, these are the sort of 6 system options for central heat pump water heaters that are available now. And there's many more coming up. There's manufacturers that are starting to get into this. The other big piece is that the 134A refrigerant and the 410A, those are HFCs, and those are due to be phased out in the coming years. And so that's the other big challenge here is we've got to both support what's available now and get ready for the transition to the low GWP refrigerants. A little bit about the heat water heater tool development. Been a lot of discussion about this, and I'll show you some of what's being developed now. So the first thing that's been prioritized by the Advanced Water Heating Initiative is the heat pump water heating sizing tool, which we call in-house the HIPWAulator. So this kind of shows, this is our beta proof of concept. It's done in Excel with some VB scripting in it. This is really designed as kind of the beta to run through how the sizing tools work. Our engineers in-house are trying to break this now. Eventually this will be released end of Q3, and this will be written in Python. It'll be open source, it'll be free, it'll be on a website, and anyone can use it. So That is the goal of the Advanced Water Heating Initiative, is to get these tools out to everyone. So this will be really exciting. This is coming into summer. So look out for this. The other big piece of this sizing tool is actually the ability to load shift, and it changes how you size. So that's the research that's happening now. Everyone's seen sort of the duck curve and what we're trying to do. And right now, the load shift, the big focus is to try to stay out of the high peak load, heavy carbon grid times. And so we're starting to look at how how to go about addressing that with design. I don't know how many folks have seen this. This is a really handy tool, the Queso net load distribution. And so we can see a month by month forecast of where we're going to have different peak on the grid. And so this is really important, because what we want to be able to do with our central heat pump water heating systems is to actually shift around these peak loads. And so essentially we're creating thermal batteries that align with a lot of the load shift initiatives. And so this will be really important and really cool stuff looking forward. I'll show you, this is some output on that beta sizing tool. And the way that it works is I entered a 100-person heat pump water heating system into our tool, and I specified when this tool would run. And so I picked a 16-hour runtime on the left and an 8-hour runtime on the right. The orange in that first graph upper left, that is the hot water draw. And if you look at the gallons of hot water per hour, that is how much water is being drawn at every hour. The blue line shows what our heat pumps are making every hour. So if you look at that 16-hour runtime, it's about 95 gallons per hour, and we're making it for about 8 hours. And so you can see that we can start to shift around when we use this, when we use the heat pump and when the loads are. And then the curve on the bottom is the cumulative hot water and storage. And that's essentially a modeling of the net effect of how much storage is left. After you get a peak draw, you run and you make a bunch more heat. So you can kind of see, where the curve on the bottom ramps up. That's where making draw and recharging the solar battery. And then it discharges. This is by doing this, we can establish how big the storage needs to be. And so in this case, feeding 100 people with the current load I entered in on the heat pump, it's 775 gallons, will allow us to shift our load around 16-hour runtime. If we go and look at the 8-hour over to the right, this is sort of, this would be a purely a heat pump set up to only operate during the solar window, so 8 to 4 p.m. And we can see that the amount of water it has to make is essentially double. Well, if we're taking 16 hours of work and trying to do it in 8 hours, well, then everything sort of doubles. And you can see the curve below. We make a lot of hot water during the solar window, and then we bleed it off until we get down to essentially zero, and then fire it back up. But that essentially doubles the storage size. So you can see the impact of that on your sizing. So the runtime is a really critical piece to how you're sizing these things. And that'll be something that'll be integral into the sizing tool. So just to kind of show an example of the two, so down on the right is a typical load shiftable thermal battery. This feeds the swing tank. So we've seen these kind of schematics before, or if you haven't, that's sort of what the system would look like. And the table on the left kind of shows the impact of the two different sizing. So if you size for 16 hours, it's 6 tons and 775 storage, has a peak draw of 6.6 kW or 120 watts an apartment. That's the real value of doing central heat pump water heating, is that our load gets distributed across many units. And so we get we can really knock down the peak draws when we go to central. And that's the argument for going to central hot water, is you get a lot of control over when you use this energy. And because of the storage, the loads are really small. But so this will be a key piece of the tool and kind of work looking forward. I do want to touch on the prescriptive heat pump water heating design guideline, or the kind of the prescriptive hot water specification that's been put out. So this was released by the California Energy Commission, mostly as a response to projects that are trying to do all electric buildings and can't get past the Title 24. We've heard this complaint a lot in recent months. So this is really kind of a temporary solution to allow central water heaters in Title 24 compliance, while the policy and the software changes are being developed. So this stuff is being developed, but this is kind of a temporary sizing tool and specification. There's a lot going on here, but for those that haven't read this section or seen this spec, this is the basic schematic that is currently allowed in Title 24 under this prescriptive path. And a couple things to kind of point out: the thermostatic mixing valves, because there's variation in the swing tank, you want to make sure you use an electronic version. The other thing that we're finding out in the PG&E lab is when you stop the recirculation pump, it impacts your accuracy of your mix. So that's something that we're looking into. Balancing where the water goes on that return pump is really important. The swing tank is really critical. Is really critical for sizing. We've got a prescriptive sizing, and I'll show you an example of that. But you've got to kind of get the size of that right to be able to extend through the non-draw periods. The storage is really important. So well-insulated storage, R22 and R10 pads on the ground. So that keeps our thermal battery well insulated, so we're not losing heat to the outside. And then the other kind of critical part to this is it's part of this kind of specification is getting the controls required to both power on and off the heat pumps and to send alarms on failure. That's kind of a key requirement with some of these systems. This is an example of some of the sizing. So using the prescriptive California sizer, I ran a 60 unit, 90 bedroom market rate sizer. We can see it comes out to about 12 tons. You do the math following this equation on the storage, it's 80 gallons per 9.7 compressors. The compressors in this case would be the sand-in water heaters. So the sand-in water heaters have the most research on them. They're kind of the furthest ahead in the technology innovation model. They've been out in the market for around 10 years, 8 to 10. And then the loop swing tank storage. There's a table in the sizing guidelines. So in this example, we've got 60 units, and that results in 288 gallons of storage. So that'll allow you a 5-hour draw, a 5-hour no draw period. And that's how that gets sized. And then the loop or swing tank usually has backup heat. And this is an area that needs more research, but the temperature maintenance loads right now, the way we do it is we look at, we've looked at about 8 or 10 buildings, and we know approximately what the losses are, and these are expressed in watts per apartment. But we typically use around 100 watts per apartment for sizing. And then we do our redundancy in upsizing that coil. And, a factor of 2.5 on that temperature maintenance will cover you for, most of the hot water draw. The peaks might be impacted. But that's to allow you some hot water while any issues are addressed. Again, this will be refined in this next iteration of the sizer, but this is available now for folks to use to actually get designs rolling forward in central heat pump water heating. I want to talk to you about some of the other tasks that are happening inside of the Advanced Water Heating Initiative. There's been this desire to develop like a plug-and-play domestic hot water systems. This is an example of a system that we're working on with the manufacturer. This would essentially be kind of a rooftop skid mounted approach. We've got a skid of heat pumps on the left, and we've got a skid of storage tanks. And so the idea here is that, in this case, we could plug in heat pumps from any number of manufacturers into storage tank skids. And so this will allow, third-party manufacturers or assemblers to put these systems together. So we're kind of aligning with, how the central gas products are. A lot of the central heat pump water heating products currently available in the industry are mostly plug and play. Some are built up, but what we're trying to do here is to get systems to the point where we can plug and play. So this is really exciting. We've got 840 units that we're looking at putting more or less 100-person skids kind of scattered around the roof. And so what this does is it drives you to roughly 60 to 70 unit decentralized central loops or decentralized loops. So one of the projects in the Menlo Park is 250 units, and we put 4 of these skids on the roof, and we crane them up, connect electrical, connect water, get that coordinated, and then plug it in. And so that's really the vision here is this results in very repeatable, predictable performance that's reliable. It's got controls, it can communicate. But this is kind of what we're talking about. And it doesn't have to be built up on a skid. This is just this particular, but working with the manufacturers and getting packages together is really going to help to facilitate kind of this grand transformation that we're talking about. It leaves a lot of the risk and the unease. It takes that out of the equation. And I think this is going to be really critical as we try to deploy this stuff. So this particular project, I've got some data from another project that we're monitoring, the Elizabeth James project in Seattle, but we can see kind of how this thing will play out. So this is a 16-hour skid design. This is like a 6.1 ton, 775 gallon storage, 6.6 kW. So we can kind of see the specs on the right. We can see how we can run this thing. So we're gonna avoid the peak rates and just run in the solar window, and then overnight at the lower rates. We can see in the graph on the lower left the COP of a system that's very similar to this, but we expect this system to deliver an annualized COP of around 3.3 to 3.5 in this particular location, which is the Bay Area. California. So this is really exciting. So this work is happening for real projects, and we're going to try to learn more about these systems. And that's what I had today.
Awesome. Thank you, Shawn. This is Panama again, the Building Decarbonization Coalition. Thank you very much for that, Shawn. I loved the mix of industry collaboration that's happening, design considerations, cutting edge tools that are coming, and from the chat, it looks like there's a number of folks that are also interested. So let me just start to run down some of the questions here.
Okay.
A question from Kevin Clark of Ream. When you talked about the overall 3 to 5 year industry goals for heat pump water heaters, you mentioned a 3.0 COP, COP of 3. Why 3? What's so magic about 3?
Yeah, that's a good point. That's a really good point. That's sort of setting the bar where we think we can get, with optimal performance in heat pumps. That sort of represents kind of the ideal case. I think that why 3? I think, that's a really good question. I would say that we chose 3 because that's a number that's achievable with good design. And I think that's really, in terms of the reduction, it also plays into a lot of the cost effectiveness calcs, but there's no real reason why it's 3. I just we've selected that because we know we can get there, and it also plays well into the savings calcs.
Great. Well, Kevin's always reaching for more, so he might be reaching out to you about this.
All right, great.
A question from Tom White. Can one heat pump water heater serve both DHW and hydronic space heating loops to a ducted fan coil?
Yes, absolutely. One thing to keep in mind is single pass equipment likes a really high lift, and multi-pass equipment only needs a 10 or 15 degree lift. And so domestic hot water loads can be served by single pass high lift equipment. Space heating loads really need to be served by multi-pass, low lift equipment. And so I would say it really, if you're aiming to do domestic hot water and then also do space heating with that same loop, I think you have to, the design changes a little bit, but your primary water heating can still be the same. And then you run your space heating through the swing tank. So yeah,
great,
absolutely.
thank you.
Yep.
We have a number of folks really interested in retrofit applications. And can you talk about the kind of the state of the market right now on central water heating retrofit projects? Where it's going, where we're at, cost effectiveness, barriers you're seeing, solutions on the horizon?
Yeah, that's a great point. I think, the retrofit stuff is obviously a bit more challenging because you get into a site and it wasn't set up to handle heat pumps, likely. With the current state of things, electric or gas are kind of the standard approach. And if you're looking at central gas systems, retrofitting those with heat pump water heaters, there's a lot of challenges there. But I think right now the focus has really been on the new construction stuff as kind of proof of concept. But the retrofit stuff is sort of being integrated now as we're starting in on this. But it's a little bit different of a challenge because of all the constraints that are happening. We've done a fair, probably 4 or 5 retrofits of various systems, and there's more pilots happening. But it's certainly an area that needs a lot more focus because of the constraints. And, the analogy I would say is that the Advanced Water Heating Initiative has a retrofit group, a 120 volt and a 240 volt. So I would imagine that the retrofit approach on the central heat pumps, which are kind of in development, is going to follow a similar path where we're going to have limited power availability. The other part that comes to mind, if you saw the size of that skid is about equivalent to a single gas water heater. And so it just shows you the power of a half-inch gas line and how much energy is available there versus what we have to do using heat pumps. And so space is also a kind of a major requirement as well. So that's definitely the kind of the elephant in the room is the retrofit stuff. So a lot of work is going to start going into that. First is to get off the ground with the tools that are needed and kind of the basics.
Great, thank you.
Yep.
From Robert, a really important parallel path that I don't see is the need to change the perception of tenants and the potential tenants that central electric everything and electric cooking are good. Most of the developers I work with are deeply concerned about leases being attractive if electric is offered instead of gas, more so for condos. Are you seeing these perceptions and biases within the marketplace and any challenges to leases from all electric designs?
No. We've done quite a few big central heat pump water heating projects in the Seattle market, and as far as we're seeing, I mean, there's utility incentives. So at the developer side, they see this as a positive because of the incentives that are helping to offset some of the first costs. The tenants, I mean, they just want hot water. And so they don't care usually how it's heated. I think the fact that they're all electric and there's alignment there. I think those are bigger market forces, saying that there's some alignment with a lot of the climate policy. No, that's a really good point, and I just haven't seen it. I mean, we put in systems that heat hot water using electricity very efficiently, and that's what we're doing. So, yeah.
Okay. We've got a question from Eric here that's getting a lot of love on the chat. What is the approximate electrical load of a central system in amps per unit? This is important for multifamily projects that have been using gas boilers because we have to add this electrical load to our initial joint trench and transformer design.
Yeah. That's a great point. And I mean, I showed you in this presentation that the skid that we're developing ends up being about 120 watts an apartment when we're, if we're running 16 hours a day. A standard electric water heater is 4,500 watts. So that's sort of the scale of or the value electrically of going to central is 4,500 watts per apartment becomes 120 watts. But we have seen, in our work, that the transformers, that's a big piece of this. New construction's easy because you can kind of get this stuff integrated. The retrofit is a much different beast because you're stuck with what you got. But there's a lot of fear that the incremental transformer costs are going to make the project not pencil. And I just haven't seen that. I mean, we've seen a small little uptick in the transformer, if any, but at the new construction level, we're not seeing a huge, there's not like another whole 500 kVA type of an adder. These are much smaller loads. I mean, if you can imagine this 250 unit apartment we've got, the total draw is 24 kW for 250 units. So you could back into your kVA on that transformer, and that would be the adder over traditional gas. So I don't think it's that big, and that's really what we're after, is trying to keep these loads down at the end of the day with these sizing tools.
Great, thank you.
Yep.
A question from Alice: will the HIPUlator be applicable to campus central plants and/or retrofit decarbonization of existing central plants?
Absolutely. When you say central plants, sometimes that means different things, but at the end of the day, what we've found is that it's the number of people that you're serving. And so the two important pieces are the number of people you're serving and what the draw profile is. And so in multifamily and in low income, we have a pretty good sense of what the draw profile is, and we know by design how many people we're feeding. And so you could essentially apply this to any hot water end use, provided you have the load profile. So what the draw pattern looks like, as well as the number of occupants. Obviously, for like restaurants, there's going to be different metrics, but for anything related to housing, this HIPUlator in its current state will be able to design pretty accurately what your sizes of your equipment need to be.
Great, thank you.
Yep.
A question from Tom Cabot: are you looking at sizing for load shifting 2 cycles per day to clip the morning ducktail and the evening duckhead? The tail is going to grow. Yep,
that's a great point. So what we're showing, I mean, that load shift sizer, you can do whatever you want, right? Because you can select. You'll be able to select when you want to run. If you want to run, and shave off both the morning and the evening peak, then you set your systems to only run during the times you want it to run, and then the program will tell you how big your equipment needs to be to get through those no run periods.
Great, thank you.
Yep.
Ben Thompson asked a question about when Colmac and Nile will be in CBEC, and I posted a response to it. There's a research version currently being tested on a San Jose project, and if it goes well, it could be released in the coming months. All subject to change, so don't hold anybody to it, and don't tell the Energy Commission. Panama said, but it's already accessible on an exception basis. And Danny Tam, who is on this call, is your contact at the Energy Commission for exceptional design considerations.
Great.
Then, just going down to the next questions. Where are people going to be able to find the HIPUlator?
It'll be on a website somewhere, and it'll be linked to anyone that wants the link. It's open source. Okay. It's written in Python. And if you want to take the code and go manipulate it, you'll be able to do that. But yeah, it'll be widely available. It's free. This is available for everyone. So this is, but look for that end of September, mid to end of September to be released.
Great. Wonderful. We'll have to have you back for a webinar on that.
Yeah.
Can you tell us the name of the Menlo Park project that you were highlighting?
Yeah, I guess. There's several projects, but it's Menlo Uptown is one of the projects.
Okay, great.
Yeah.
Got a three-part question here. Can you explain load shift again?
Yep.
Question 2, how are designers handling the higher FLA draw now that buildings are going to all electric? And then, is this presentation recording available? And I'll answer the last one.
Yes.
So can you explain load shift again? And then how are designers handling the higher FLA draw now that buildings are going to all electric?
Yeah. Okay. So load shift. Load shift is really, if you were to let a heat pump run whenever the tank got low, you would essentially run your heat pump after your big draws. I mean, that's how most hot water heaters work. You run a bunch of water, that will trigger the draw. With load shift, you want to control when you run your equipment. And so what you'll do is you'll add more storage to get you through an event that you don't want to run. So it's really being able to control your domestic hot water load and run it whenever you'd like. So you're shifting that load. You're shifting when you run your equipment to be optimized for how you want to set up. The question about the higher energy draws and how are designers dealing with this? Well, I think that it's not just heat pump water heaters that are part of this. We're also looking at space conditioning and also potentially plugging in cars. And so when we bring over space conditioning from traditional gas to electric heat pumps, those are going to impact the grid as well. So it really is like in new construction, it's easy. You add up the loads, you go to the NEC, you look at what's allowed and how you do your calc, and then then you go pick the transformer that you're looking for. But I don't think it really changes anything. It's, the load is the load and you have to design around it.
Great. Lightning round, will the HIPUlator be applicable to other building types beyond residential?
That's the goal. But first, what needs to happen is we have to understand the load shapes, and then we can plug those in because that's an integral part of sizing. Okay,
thank you. And then the last 2 questions, see if you can fit them in a minute and a half. One, Can you talk about the cost effectiveness of central heat pump water heater system compared to a central gas system? 1, and then 2, what we learned about working with central heat pump water heating systems?
Oh boy. Okay. I get a minute. Okay. Let's see. So cost effectiveness, this is definitely, the topic of the hour. And, being that heat pump water heaters are new, the market is not, the pricing and the market is really not, it's not there in terms of getting these costs down to the level of gas. But when you run the cost effectiveness calculations and you're looking at kind of the time of use, TDV stuff, the heat pumps are kind of a slam dunk in terms of the carbon impact on the grid. So, but the bigger challenge that we've got now is to get the designs out and to get the industry up to speed on how these go, and then we'll see the costs come down. But right now, I mean, we're still doing projects now that are cost effective in Seattle. There are incentives in play that essentially make the cost of these things almost cost neutral if you look at all of the costs included in kind of your base case systems. But it's certainly an area that is of high focus, and so we're continuing to look at that. But certain scenarios, these systems are definitely cost effective, and we continue to kind of work on that with more deployment.
Great. And then big lessons learned, you would say, to wrap it up.
Yeah, lessons learned. I would say, I mean, there's a lot of lessons learned. We learned a lot of our lessons in this stuff by making mistakes. And we're trying to not repeat that on a grand scale. And so the lesson learned is really that you have to put the due diligence in understanding your equipment, understanding the design problem, and really learning from different things that happen. I mean, we're still learning about how these systems work. We've done about 50 or so designs, and we're at the point now that no building size really kind of scares us. It's really just scale and and repeating. But there's a lot of lessons learned, and I think it's really that taking a very strategic approach to how you implement new technology is really crucial to the success of those designs. And I think that's kind of like gets all the way back to kind of the scientific method and how we approach problems. But that, I think, is the biggest lesson learned, is that everyone's eager to try new stuff out, but you really have to go through the kind of the due diligence on this stuff to really understand how it's going to work and to really be successful in deployment of central heat pump water heaters.
And who's done a lot of the most of the due diligence? Shawn Oram, right here, Ecotope. Yeah. That's his email address on the screen. Feel free to reach out to him to follow up at all. Feel free to join the Building Decarbonization Coalition to get access to more of these presentations. And thank you so much, everybody, for joining the webinar today. We're really excited about so many people interested in electrification and pushing it. And I want to say thank you for all your efforts out there. Let's keep it up, and we'll see you on the next webinar. Thank you, Shawn.
Thank you.
Good work.
Yep. Thank you, everyone.